Hello everyone. In this video, I'm going to show you briefly how to do demagnetization analysis in Flux using new material definition, and also how to use new tools for reusing magnet materials after demagnetization.
Now let's look at an example. Here I have considered an IPM machine with 48 slot 8 poles. Now we'll create a new material, and here we need to consider a nonlinear magnet type. And here we have changed the inputs that you need to give. So they are remnant flux density, normal coercivity. You can see the representation on the graph on the right, and intrinsic coercivity based on the temperature at which you're considering your material is operating, and then the transversal relative permeability. Update your resistivity to compute accurate eddy current losses, and then click OK. Now this will create a nonlinear magnet material. We have to assign this material to magnet regions. Then we have to complete the orientation. So assign their respective coordinate systems and the angle of orientation. Now once this is completed, you're ready to solve. So but before that, you can look at the magnet orientation also to confirm. So they're good. Now we can go ahead and solve it. Save your project and then continue with solving. Once the model is solved, now we can look at the demagnetization. So we have a post-processing function where you can see demagnetization. So there you select all the phase regions and select the period. Now give your name and then what is the threshold, that means the knee point. And then for this one I considered as 90%, but based on the characteristics you can choose, and you can see 41% of volume of magnet is demagnetized. And we can also look at it more in detail by plotting the ISO values of BR that's computed just now. So select your magnet regions, and then when you do evaluation, there's a new spatial quantity created, which is BR min, same name. And once you select and click OK, you can see the graph, the plot of the BR on the magnets, and one with same value as BR, initial BR are not demagnetized, and the area lower than that is demagnetized. So that's what you can see. Now we can plot torque as well, and you can see that the electromagnetic torque mean value is 220.4. And here you have to remember that we did not take the demagnetization into considered into solving process. Um, so whatever demagnetization that we did, it's from the post processing. It's not considered in the solving process. I'm exporting the torque value so that when we solve it with demagnetization, we can bring this torque curve into the solved project, and we can compare. So now once we save it, we can rerun the model with consideration. So I am deleting the results, and now we have to go to magnet material and then select taking into account demagnetization during solving process. Now that is done, you're ready to solve. So we can solve the project. Now, after completion of solving the project, we can plot torque again. Now you should see a lower torque because now we are considering demagnetization. So you can see the average value is 214, whereas initial one was 220. So I'm imputing the initial one so that we can superimpose and check. And selecting both the plotted one and imported one. And if we superimpose both of them, you can see the difference that the initial one torque values are little higher compared to the one plotted with the demagnetization. So that is what you can see um, reflected in the mean value as well. And now let's look at the new features that we included to reuse magnet materials after demagnetization. So you need to go into data exchange. Under magnets, you'll see two options. One is to export BR as a JSON file. So if you click on it, you can give a name to the JSON file and then the material, choose the material. And now if you click OK, this will export the material as a JSON file, which you can reuse it in the Flux project. So now I'm just saving it as so that we can bring the material. So yeah, now let's delete the results. And then, so under physics, material, you'll see an option to import JSON file. So click on it, give it a name, and select the material that is created as a JSON file, and then open. You don't need to select any, it will take the reference or the global coordinate system, and then click OK. Now this will create a new material with the name that you have given, and this is as created as a spatial quantity, and this spatial quantity you can see it under parameters and spatial quantity as well. So that will be there, which is called into the material that is newly created. Now we need to give this material to the material regions. So edit and then here. And since this is a spatial quantity, you don't have to orient it. Orientation is already defined in there, so you can directly see by displaying the arrows. So you can see that the demagnetized material is imported and mapped onto the magnetic phase regions. Now with this, you can solve it. And now after solving, you can directly plot your torque to look at the mean value, and this will be same as how you got it with demagnetization considered. And also you can see it's almost similar. Another tool that we have is reuse. So this will create a new project containing the new spatial material directly without you exporting and importing the JSON file. It will do everything directly and it will recreate it. And you can use this for transient magnetic applications, whereas the other feature of exporting the JSON file can be used for both transient magnetic and also magnetostatic projects. After solving the project, similar to the other ones, you can verify it with by plotting the torque. You should get similar torque as how you got as demagnetization considered. Thank you.